Hello, everyone. We're going to start our conversation and lecture about energy, and it starts with relating energy to work and then comparing and finding the connection from work to power. Okay, so first, way back in our earlier units, we talked about how Newton's second law, force is equal to mass multiplied by acceleration. And if we want to solve for acceleration, we just divide by mass, right? Force is mass. Force divided by mass equals acceleration. And I pulled this equation from our kinematic equations, where d is displacement, delta x, okay? And so what we're going to do is we're going to take our acceleration, force divided by mass, and we're going to plug it in right there. So what we end up with is 2, and then we have force, and then we have displacement over mass, velocity final squared minus velocity initial squared. Okay? And what we want to do is we want to get force and displacement by itself. So we're going to multiply both sides by mass, and then we're going to divide by 2. And so this is what we end up with here. We have a force applied over a distance, okay, and then 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. Now, there's some equations here that you may not recognize. The first one being work. Work is force multiplied by displacement, like for how long, for what distance was that force being applied, okay? That's work right there. And so we can plug that in, right? We can replace that. And then 1/2 mass velocity final squared. Well, 1/2 mass velocity squared, that's kinetic energy. So this would be kinetic energy final minus kinetic energy initial. Right? This would be kinetic energy final minus kinetic energy initial. And so final minus initial is just the change in. So work is equal to the change in kinetic energy. And the work energy theorem tells us that if we have a change in energy, not just kinetic energy, but a change in energy, then we have work. Okay, so let's add that off to the side here. Work is a change in energy. And that could be a change in kinetic energy, and that's what we just proved there, but it could be a change in other types of energy too. The other one that we're going to focus on today is potential energy. So we had kinetic energy, okay, and then potential energy is mass multiplied by the acceleration due to gravity, 9.81, and then the height of the object. Okay? So, work is a change in energy. And we've defined 2 different types of energy. So it looks like if something has mass and is moving with some velocity, then we have kinetic energy. If something has mass and is at some height, it has potential energy. Okay. Now, what units would that be? We have work, which we've defined as a force multiplied by a distance. Well, a unit analysis of that would be newtons and meters, right? So we'll take a newton, which is a kilogram meter per second squared, and we'll multiply that by meters. Put it over 1 to see that fraction. So we have kilogram meter squared per second squared. And a kilogram meter squared per second squared, that is a joule. We should put this, so this is a Newton meter. That should look familiar to you. Newton meter, that's how we defined torque, right? And now we're looking at work. And work and torque are really interesting, and they have lots of interesting similarities. So reminder, torque was force perpendicular multiplied by R. So if this pen, if I apply a perpendicular force to the distance away from the point of rotation there, if I apply a perpendicular force, we get angular displacement, but not linear displacement. Okay, so a perpendicular force causes angular displacement, causes rotation. So torque causes rotation, but work causes linear displacement, not angular displacement. And no matter how much I push on the pen perpendicular, the force perpendicular, I don't get any linear displacement. Linear displacement has to come from a force that is parallel to the motion of the object. If the object's going to go that way and the force is pushing that way, right? So unlike torque, it's the parallel component that gives us a linear displacement. Now, what you're going to encounter in this class is that each time I'm going to give you either the force, it's completely parallel, maybe it's completely perpendicular. In that case, the parallel component would be 0 and there wouldn't be any work done. So be mindful of that. Let's continue. So work is force multiplied by distance, so that is a joule. We also talked about work being a change in energy. So we had kinetic energy, which was 1/2 mass velocity squared. Okay, so as far as unit analysis goes, 1/2 unitless, mass kilograms, multiplying this by meters per second squared. So that would be kilograms multiplied by meters squared, second squared. So we'd end up with kilograms meters squared per second squared, and so that's a joule. Okay, so energy and work have the same units, and the change in energy is work. Let's look at our last one here. Potential energy, mass times by acceleration due to gravity times by the height of the object. So that would be mass, which would be kilograms, multiplied by acceleration due to gravity, meters per second squared, solved by a height, which would be in, or multiplied by height, which would be in meters. And so end up with a kilogram meters squared per second squared. Okay, so we get a joule each time. So a joule is the units for energy, for change in energy, and the change in energy is work, so it's the units for work as well. Now, like I told you, we may apply a force at an angle, and what if that force is perpendicular to the lever arm, then we would have, and then that would cause a torque. But if the force is parallel, the parallel component to the displacement vector, that's what causes work, an object to see displacement with a force being applied. Okay. Now there's another way that we can calculate work, and that's with a force versus displacement. So we have this equation. We know that work is force being applied over some displacement. I'm applying that force over that entire displacement. But this is a constant force, okay? And so that's what's seen in this graph. We see a constant 20 newtons force being applied over a displacement of 1.5 meters. Now, when I take force, I multiply it by distance. So I take the force, 20 newtons, and I multiply it by the 1.5 displacement, I get 30 joules. Notice that the area under the curve is the same because it's base multiplied by height. So this area, this gray area here under the curve, is also 30, and we took base meters multiplied by height newtons, and that would give us joules. So this area under the curve is also 30 joules. So it turns out that when you take a force versus displacement graph and you calculate and you find the area under the curve, that is the work as well. So this is a nice concept because force isn't always constant, and usually it's not, right? That it tends to start as nothing, and then we increase our amount of force as the object moves away. And so we can use a force versus displacement graph to solve for the work that's being done. In this case, we got a triangle, so we could do 1/2 the base multiplied by the height. So there was 15 joules of work done in this situation. Now, here's a graph that we have a force versus displacement there, and we can calculate the work done by the object that's represented, or not by, on the object that's represented by the graph there, okay? And so we would just look at the area under the curve. So here, let's calculate this part first, right? So we have base is 4, height is 10, so that would be 40 joules, okay? And right there, from 4 to 8, so that'd be 4, base is 4, height is 5, so that'd be, that'd be 20 joules. But we have a triangle, so base is 4, height is 5, so half of that base, 2 times by that height, so we'd have 10 joules there, and then another 4 multiplied, 8, yeah, 4 multiplied by 5, and then this one's a little bit different, 12 to 14, so the base would be 2, so half of that would be 1 times by the height of 5, so that would be 5 joules. Now I'm just going to add all that up together because that's the area underneath the curve. So I'd take my 40 joules plus my 10 joules plus the 20 joules, and 5 joules. And I get a total work that was done on this object would be 95 joules. Okay, let's move on to the examples here. So, example number 1. Let's read through this, and then I want you to give this a go, and then we'll come back to the next video and we'll do the work together. But I want you to try it on your own first. A 105-gram hockey puck is sliding across the ice. A player exerts a constant 4.5 Newton force over a distance of 0.15 meters. How much work does the player do on the puck? What is the change in the puck's energy? Okay, give that a go, and then join me on the next video. Let's see if we got that done correctly.